today we have the privilege of having James Mayfield. He's a senior computer scientist at the Johns Hopkins Applied Physics Laboratory down in Burtonsville or Laurel, somewhere like that. Laurel, thanks. He did his PhD from University of California, Berkeley on plan recognition for dialogue systems. After that, he was at UMBC, where he was associate professor of computer science. Since then, he has gone to APL and worked on several interesting things. Today, he's going to talk to us about his work in cross-language information retrieval, and in particular on the system they developed there recently called Haircut.
Hi, welcome. The title of the talk is the Haircut System for Cross-Language Information Retrieval. That is perhaps slightly poorly worded. It's not really a system for cross-language retrieval. It's an information retrieval system which we are applying to cross-language retrieval. But I'm going to talk about information retrieval in general first to bring folks without a background in information retrieval up to speed. Then I'll talk about our system, which is called Haircut. I'll tell you why momentarily. Then I'm going to talk about two more specialized topics. One is combination of evidence, how we use the results from multiple retrieval runs to improve our performance, and then talk about how we use it in cross-language retrieval. Okay, so information retrieval. What do I mean by information retrieval? Well, what I really mean is text retrieval. Okay, we don't. That's sort of the traditional notion of information retrieval is you have a big wad of natural language text. You index it. Somebody comes up with a query. They type it in. You get back a bunch of articles, just like you might with Alta Vista or Google or something like that. So the user's query is in natural language, say English. The system in the olden days used to just return a big wad of documents, but these days those documents are ranked so that you get some notion of where the system thinks these documents ought to be in the grand scheme of things for this query. And that's sort of what the system is supposed to do. We'll see if we get this. This is what more typically happens is here. And I was going to bring a chocolate bar to award the person who could identify this sound clip, but I forgot it. So you'll get a brownie if you can identify it. It's a little loud. You recognize it?
Where am I?
Yeah, somebody back there.
What do you want? Information. Whose side are you on? That would be Penny. We want information. 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 You won't get it.
That's what typically happens. You go up to Alta Vista and you're looking for information and you won't get it because the system performance is really pretty poor in many cases. And I'll talk a little bit about why you won't get that information and what can be done about it. First, I'll talk a little bit about how information retrieval researchers typically view the problem. So the first thing that an information retrieval system does is to characterize the documents in the queries. And typically that's done, in most cases, by using words. So the system will take a document, chop it up by white space, do some other processing. Sometimes the terms will have their ends chopped off. That's called stemming. The purpose there is to make things like words that are related, juggles, juggling, jugglers, juggled, make those all map to the same term. Some systems will do that. On the web, often systems won't even do that. But you end up with a bag of words. It's just a document that's described by just a collection of words with no ordering information. The queries are similarly characterized so that the person's query gets put into the system, gets chopped up into words, and the query then is treated as another bag of words. And you're interested then in matching one bag of words against another. The use of words has a number of advantages and disadvantages. Most traditional systems will use words as their indexing terms. I think I will stand over here so I can not look back all the time. There are a few problems with word-based retrieval. One, it is typically language specific. That is, if you put any smarts into your system to break up the words, like stemming, chopping off the ends of words to conflate terms that are relatively close, those rules that you put in are going to be language specific. They're going to work for English, but they're not going to work for French or German, and certainly not for a language like Chinese where you don't even know where the word boundaries are. Okay, so a lot of the effort in a word-based system will go into something that's language specific. Another problem with word-based systems is that they tend to perform poorly if the documents aren't pristine. Okay? So if you have a collection that's been built from OCR or transcriptions from audio, those things tend to work less well with a word-based system, because an error in a word, if you have like an OCR error in one character of the word, that word is gone as a useful indexing term. So there's a competing technology called n-gram technology. You've probably all heard of n-grams. We're talking here about charactergrams, not wordgrams. So one way to characterize a document is to break it up into overlapping sequences of characters. Okay? So if your text is 4^7, the first 5 grams, say, is FOUR blank. The next one's OUR blank S, and so on. Okay? Now, that seems a little counterintuitive. What's the semantic content of UR blank SC? It's not very high. Okay? But it turns out that if you use n-grams as indexing terms, they actually work quite well. And there are a variety of reasons for that. One is that they span words. So you were getting some of the information about word collocations it's not simply a bag of words representation that you're using. There's a little bit of information in there about how the words go together. N-grams are language independent. It doesn't matter what language you're using. Maybe the value of n changes with language, but overall the technique itself, you can plug in French, German, you can plug in Chinese, you can plug in machine binaries. We're doing an experiment with using binary code and indexing it using these techniques. It doesn't matter what the underlying language is. You can always break it up into n-grams and use those n-grams to index the technique, even if you don't know where the real semantic markers are in the text. N-gram takes, yes?
Are you assuming that the query is also a text? Because if you just put 3 terms there and you extract the n-grams, I mean, the boundaries will not have any meaning for it.
Yeah, okay, good point. The question is if you have a typical short query where the words aren't related in some natural way, then the n-gram technique is not going to be particularly successful there. So we actually tend to work with longer queries where you do have real language. Yeah. Another good feature of n-grams is that they are very robust against errors in the text. So take your OCR text. It's got an error right in the middle of it. The word is gone as a useful indexing term, but the n-gram on this side of the word and the n-gram on this side of the word are still there, still valuable as indexing terms. So someone actually from NSA did an experiment where texts were degraded up to 30%. So 30% of the characters in the text were either deleted, changed, or had a character added to them. You look at these texts, and it's almost garbage. You almost can't make it out. And you do retrieval based on the n-grams, and being the first one is the undegraded text, the next one is the 5% degraded text, the next one is the 10% degraded text. It's really phenomenal. So they're very good in certain situations where you have a lot of noisy data. So those are some of the features of n-grams. And so there are these 2 competing technologies for characterizing the documents and the queries, words and n-grams. Okay? Once you have those characterizations and you're interested in retrieving text, you need some way to measure the similarity of each document to the query phrase. And once again, there are a variety of competing techniques. The classic technique is to view each document as a point in a high-dimensional vector space where each dimension corresponds to one of the possible words. Okay? So if you do this, then a document that has says green frog will have extent 1 in the green direction, extent 1 in the frog direction. So it'll be a point up here. If the query is blue frog, well, that query will have 1 in the blue direction and 1 in the frog direction, so it'll be up here. Okay, so you have 2 points, one for representing the query, one representing the document. You need some similarity metric. Euclidean distance is not particularly good because you run into problems of normalization and so on. What people have typically done is use some sort of cosine measure where there's an angle going from the query to the origin out to the document. The cosine of that angle is used as a similarity metric. So the higher the cosine, the closer those two are to each other. The lower the cosine, the farther apart they are. That's a classic technique. It's the basis of, for example, the SMART information retrieval system, which was the classic system out of Cornell. There are a variety of competing probabilistic similarity metrics. And the one we use is, I'll call it a hidden Markov model. It's billed as a hidden Markov model. If you actually look at this thing, it's not quite a hidden Markov model, but let me go through it for you. There is, in this way of looking at things, you are interested in calculating the probability that a document is relevant given a query. Okay? So we apply Bayes' rules and say, well, we will calculate that by calculating the probability of the query having been generated giving this document is relevant times the prior for the document divided by the prior for the query. Okay? Once we've done that reduction, then we make the following observations. In a single system with a single collection, the prior probability that a document is relevant can just be thrown away because we'll just assume it's uniform. Okay? Now, in fact, not everybody does that. There is reason to believe that if you have reason to believe that certain types of documents are more likely to be relevant than other types, you can plug something in here. But typically, that term just gets thrown away. The prior for the query, what's the likelihood that this would have been the query, is likewise thrown away. Why? Well, you don't have any reason to believe that one user is going to walk up and issue one query versus another. Okay? Now, when it comes to cross-language retrieval, that's a big problem because when you translate the query, you don't want to end up with, you may have a different prior for the query in another language, and it gums things up when you try to merge the results, but I'll talk about that later. But it's sort of as a baseline system, these things get thrown away, and you're left with trying to calculate what's the probability for this query given that you know the document is relevant. Okay? So we can build a little dinky hidden Markov model that has 2 states. One, and the purpose of this model is to generate the query given that you know that the document is relevant. So it has 2 states. One state is responsible for spitting out words that are in the document. Okay? Another state is responsible for just spitting out query terms at random. A query gets put together by running through some pathway through this thing, and this is an epsilon transition from here back to here. There's it's not really a hidden Markov model, so for your perfectionists, you're going to quibble with this. But this is how we think about it. This is the reference for anyone who's interested. And so a query gets generated by zipping through this thing. Sometimes a word gets generated just because it's a good query word. Sometimes it gets generated because it's important to that document. Okay. So how do we get the statistics for these? Well, to get general query English, we simply take a large corpus of language, use the statistics from that corpus and say, this is our canonical representation of English at large. We'll use the statistics from that. Here we use the statistic of the document. The probability that a term gets generated is simply its frequency within the document. Okay? Once you have this model, you calculate the similarity metric like this. The probability of the query, given that the document is relevant, is simply the product of alpha, which is some training parameter, times the term's probability of being generated here, plus 1 minus alpha times the term's probability of being generated just as a general language, general query English word. You multiply all those probabilities together, 1 for each word in the query, and that's your total measure of the similarity between the query and the document. Okay. So that is a competing method for judging similarity. So now we have two types of indexing terms. We have two similarity metrics. Which is better? N-grams of words, vector model, hidden Markov model. The answer is better. What do you mean better? Okay. We need some kind of metric to assess how well we're doing. So let me talk about how that is done in information retrieval circles. There are two notions that are used in information retrieval called precision and recall. And these deal with, I mean, there are lots of names for these in different fields. Some people call them type 1 and type 2 errors. Rock curves is another one for this kind of curve. But basically, we're trying to measure two things. Given that we retrieve a bunch of documents, one question is, how good are those documents? Are the documents we get back very relevant, or are most of them irrelevant? Okay? That's a measure of precision. For the documents you get back, the larger the number of those documents that are relevant to your query, the higher your precision. Okay? There's another metric that we use, which is what percentage of the relevant documents did we actually get? Okay? So if we got back 100 relevant documents, and there are actually 200 relevant documents in the query, then we've only gotten back half of the relevant documents. That's called a recall of 50%. Okay? So there are these two measures, and you will often hear people talk about, oh, this is a recall improving technique, or this technique is aimed at precision. Whenever you hear something like that, you should be very, very suspicious, because it makes no sense to talk about one of these measures without talking about the other. The reason is that I can right now build you a system that will give you 100% recall on any retrieval task you want. Okay? I'm simply going to build a system that returns all documents. Okay? I do that? Well, I've given you all the relevant ones, haven't I? Okay? It doesn't make sense to talk about recall if you're not also talking about precision. Likewise, you can usually improve precision by returning fewer documents. Okay? So it doesn't make sense to talk about these two measures independently. So we always talk about them together, and we use a precision recall curve. We assume that the system is retrieving a ranked list of documents, and we sort of march down that list. Every time we get another relevant document, we say, okay, now we've gotten n% of the relevant documents. What's our precision at that recall level? So that gives us a curve that looks like this. What we want this curve to look like is straight across the top. Okay? In practice, real information retrieval systems get something that looks more like this. Usually it ends up hitting the left-hand side over here somewhere. We can boil this down to a single number by taking the area under the curve. We call that average precision. That's the most commonly cited single number measure of an information retrieval system. How do we actually take advantage of this? Well, there's a contest. They don't call it a contest, but it really is. It's called TREC, the Text Retrieval Conference. And what they do at this thing is anybody who has an information retrieval system that they want to compete against all the other folks enters. You get shipped, well, up until this year, it was 2.5 gigabytes of newspaper articles. Next year, it's going to be 10 gigabytes of web data. So they're scaling it up. But up until now, it's been 2.5 gigabytes of newspaper articles. You get your system to index it, and then at a certain time, they release 50 queries. You run each one of those queries through your system, retrieve 1,000 documents for each one, and ship them on off to NIST. And they hire retired NSA and CIA analysts to sit down and slog through the results and score your system. And then you compare your results against those of others. It's, the purpose of the competition is to stimulate research. It's not really a gloating thing. In fact, there's a no-gloat rule. You're not allowed to use any results in advertising or anything like that. But we did well then. Trek also has a number of different tracks, some of which might be of interest to people here. Here's a document routing task, a very large corpus that does 100 megabytes of web data. The one I'm going to talk about today is the cross-language retrieval, where you put a query in say, English, get back documents in English, French, German, and Italian. So there's some kind of, you have to do some kind of mapping from one language to another for that. And another one that might be of interest to folks here is the spoken document retrieval track, where you get some number of hundreds of hours of, I think it's news reporting. And you have to go from the audio there, transcribe it, put it into a retrieval system, and then retrieve based on English queries. That's a track that you can enter. If you're interested, we can, but you don't have an IR system. We've got one. We can talk about it. Okay, so that's how we actually do the evaluation. This is a sample topic. Trek topics come with a bunch of different pieces. There is a short 2 or 3 word phrase that describes the essence of the query. There's a sentence level description, and there's an entire paragraph. And you can base your retrieval on any combination of those. We typically use the whole shebang. Our techniques work better that way, but as most techniques do. Just the topic would be more representative of a web query. So that's sort of a brief overview of information retrieval. I'm going to talk about our system now, which is the haircut system, which is the Hopkins Automated Information Retriever for Combing Unstructured Text. It's a system we built over, I guess, the past 3 years at APL. It's written entirely in Java. It used to be written entirely in Java. I'm enamored of Perl right now, so there's a bunch of Perl thrown in there. It supports a variety of indexing terms, including n-grams, words, stemmed words, multi-word phrases, and so on. It has a variety of similarity metrics, including a normalized cosine measure. The cosine itself, you do various things to it to make it a little nicer. So we have, and those are pretty standard. So we can do that. We can do this hidden Markov model, and it works successfully on the 2.5 gigabytes of text that we have to index for Trek. It will work successfully for the 10 gigabytes that we're going to have to index. We haven't tried that much yet, but I can't imagine we'll have any problem because Java has come a long way in the while. This is we. The only one you might recognize is Paul McNamee. He was an undergrad here a few years ago. This is our performance on last year's Trek. Our average precision was 34.5%. This is, I guess we were 6th by this measure. I think the top system was like 33. This is the median system at last year's Trek. So I put this up to show where the power of our system is, which is down here. We typically just sort of do run-of-the-mill up at the first page of results. This is the area over here that you want a web search engine to do well in, because nobody looks after the more than 2 pages of web search results. But we've been focusing on the whole thing, not just trying to crank up our numbers over here. And we do really well down here around the 70–80% recall level, where you're really interested in trying to find everything on the topic. The haircut system does very well. We've done a number of experiments examining which is better, words or n-grams. Our initial experiments under a cosine measure a long time ago seemed to indicate that n-grams were actually significantly better than words. We've done some with our system is much higher performing now than it used to be. We've rerun these results. And this shows you a comparison of how words do against n-grams on the Trek 8 task, everything else being held constant. Okay, that is, it's the same lexical analysis of the words, same similarity metric, and everything. In fact, it's so similar, we even use the same training alpha for both, which is absurd because n-grams actually respond much better to a lower alpha. And so these probably undervalue the worth of n-grams as indexing term, these charts here. We'll rerun that. But what the graph shows is that you can't even see it on the projection. 2 grams actually have a little blip. A long time ago we did 1 grams, which is single characters, and it was actually slightly better than random. It was unbelievable. But 3 grams is where most of the classic literature in n-grams has looked. And you can see 3 grams are very poor for performance compared with 4, 5, and 6 grams. We have been using 6 grams. Our earlier tests show them having a slight edge over 5 grams. Our more recent tests show 5 grams having a slight boost. But I guess the point of this is that n-grams are very much on par with words as indexing terms. And so under circumstances where n-grams are going to be particularly good, they're a very reasonable way to go. And I'll talk more about what circumstances those might be. Let me skip this. So that's one question. What's better, words or n-grams? We also compared the cosine measure against this hidden Markov probabilistic measure. And we have always found a significant outperformance by the hidden Markov model over the cosine model. Okay. Now there are still very, very good systems that use a cosine model. It's an information retrieval system is a bundle of a whole bunch of things. If you just put basic terms and a basic similarity metric and say go, your performance is not going to be very good. There's a lot of hackery that has to go into to putting together a high-performing system. And so to what extent is these systems' performance due to their other stuff, and to what extent is it due to their similarity metric? It's not clear. My suspicion is that they are overcoming this discrepancy with other techniques. So now we have the question, once again, which is better? N-grams or words, vector model, in Markov model? The answer is it depends. Okay? But we really feel that for our purposes, the answer is both. That is, we find that by using both words and n-grams, by using both a cosine measure and a hidden Markov model measure, we get results that outperform any single technique. Okay, so I'm now going to talk about combination of evidence, which is how we go about taking the results of several different runs using different indexing terms, using different similarity metrics, and put them together. Okay. So our basic retrieval strategy for doing this is we build 2 kinds of indexes, one for words, one for n-grams. We search for relevant documents using cosine measure once, using hidden Markov measure once. We take the various results and we merge them together. This is what we're merging. These are examples of the kind of output that Trek expects. You have a topic number, you have a document number, its rank, and its score. Okay? So we take these as the input to our merging software and merged based on that. There are a variety of strategies you could take for combining various different runs. You could take a round robin approach where you just take one from here, 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 and so on. You could do weighted round robin where a run that you think is better gets a little more weight. You can do it by score and take the maximum score for any document is its overall score. You can do minimum score. You can do a linear combination. There's lots of ways you can combine. We actually use a linear combination to put these together. So we take the scores, we normalize them, and then we put them together. This graph shows the effect of doing this combination. It shows 3 underlying runs. This is a 6-gram run using a cosine similarity measure. This is a 6-gram run using a hidden Markov model measure. This is a word stems, which is the words with the ends chopped off, as indexing terms using a hidden Markov model. And you can see that the precision recall curves we get for those 3. We do a simple linear combination of 2 parts this score, 2 parts this score, and 1 part this score. And we get a curve that is significantly above the other ones. It's, I guess it's 2.5 points above, which in Trek terms is a significant jump. Okay? So you can see that you get a big boost for combining evidence. This is not really new news. People have done combination studies for a long while. But what we found that I thought was interesting is that to get these results, you don't have to have wildly disparate systems. You can have a single system. The difference between the code for doing these 3 runs is a couple pages at max, not including the stemming softwares we just sort of ripped off from the smart system, and that's a little longer. But we do this with just raw words too, and we get very similar results. You can have a system that simply changes a few very small things in the code, comes up with different output, and combine those, and you get a huge boost in your overall performance. This graph shows what's actually happening underneath that previous graph. All the precision recall graphs you've seen so far are averages over all 50 queries in the Trek test. This shows a query-by-query analysis of how the combination works. So this should probably be a bar graph, but it didn't fit. Each column here represents a different Trek topic. They're sorted by median score. That is, there were 40-some systems that participated in Trek. We just took the median score on a query-by-query basis, sorted them that way. And what you can see for any given query is that there's a big variability in how the different techniques perform. Here's one where the cosine measure is absolutely abysmal. The combination, blue here, is better than any of the individual ones in that case. Because why? Because just the combination of evidence basically overrules this one. That's not always the case. Blue isn't always the top one. Here, 6-gram HMM slightly outperforms the individual, the combined score. But what's interesting is that the combination always hangs out near the top here. Sometimes it's the very top, but it never really suffers, with maybe a few exceptions. Okay, it almost never suffers from cases like this where there's scores that are really significantly above it and it gets dragged down. This presumably is because this score is so hideous. Another thing this chart reveals is that the relative strengths of the different techniques are not uniform over the possible queries. That is, a given query may respond much better to one technique. Another query is going to respond better to a different technique. Okay, so it's important when you look at these kinds of Trek results that you not get lulled by the fact that you're looking at aggregate numbers. That occasionally you actually look at the underlying numbers and see what's going on. So that is all by way of prelude to talking about cross-language retrieval. The idea behind cross-language retrieval is that you have a query in one language and you have a document collection that comes from 2 or more languages. Or, well, maybe one, but it's a different language than the query. And somehow you have to map that query into something that can be searched for over in the documents, or you have to map the documents into something that looks like the original language. The Trek cross-language task last year was a collection of, whatever that adds up to, of something over a couple gigs maybe, of text from 4 different languages: French, German, Italian, and English. The results were judged by 4 different teams, and from USA, Germany, Italy, and Switzerland. Why the French couldn't do the French, I don't know, but the Swiss did that. And in every other respect, it was like the basic Trek ad hoc retrieval task, except that instead of just returning a list of documents from one language, you had to pull in those documents from all 4 languages that that you thought were going to be relevant. If you had a query and all the relevant documents were in one language, then you want to return results from just that language. But if they were spread out, then you want to return them from several. Okay? So for this reason, a technique like round robin is not a great technique to the extent that the answers are language specific. So if you have a query where all the relevant documents are in French, and you're doing round robin, you're doing, okay, no way, no way, no way, okay, no way, no way, no way. So this merging is, how you do that is an important question. So, and in fact, I got a little ahead of myself. There are a number of important questions. And this diagram represents the basic task of going from an English query to a Trek result set. You have the question of how do you map the query into the various foreign languages? Okay? And I'm making the assumption that we're going to map the queries and not the documents. Some people map the documents. They just take all the documents in the other language, translate them in English, do regular IR. That's fine. It's not clear that that scales very well. And the folks who have done it have not shown any significant performance improvement for doing that as opposed to translating the query. So given the query, how do you map it into a query in each of the foreign languages? How do you solve the basic ad hoc retrieval problem in those languages? And then once you have results in each language, how do you combine them? And here's our approach to it, which is just as basic as we could get. We use commercial translation software just to translate the query in our base system. We actually do some more interesting things as add-ons. But basically, we take Systran, which is this commercial package. You can buy it for $100 or something. We run the query through it to get French, German, and Italian. We have a separate version of Haircut for each language and indexing documents for that language. And then, so we get results from each language, and we use this linear combination technique to combine the scores. How do we do the combination? Well, each language is represented by a separate collection, and so we have a problem of what kind of indexing terms do we use, what kind of similarity metrics do we use, and we boil this down to having 2 indexes for each language. So we built a word index and a 6-gram index for each language. Why 6 grams? Well, because 6 grams work very well in English. We didn't test the other languages. It's very conceivable that different values of n will be better for different languages, but we didn't. We did this on a very tight calendar, so we just picked 6 grams. We then weighted the value of those different of the word retrieval versus the n-gram retrieval differently in the different languages. Okay, so for English, for example, our tests at that time were showing that on the collection that was being used for cross-language retrieval, words worked significantly better than 6 grams. So we weighted the word results 3 times the weight of the 6-gram results. That was very different in German. In German, 6 grams worked significantly better than words, and I'll talk about that in a minute. So we had these within language weights, and then we also weighted the languages to indicate that, well, English results are just better than the results in the other languages. Italian was worse. The reasons for that are complex. Other sites found this. It had in part to do with the quality of the retrieval in that language, but it had more to do with what the actual queries were, what the collection was like, who the assessors were. It's a very messy business, IR, and so you can't. It's hard to draw. It's hard to draw conclusions from things like this without having tried it over several years. Okay, so this is the. We had some training data from the previous year's Trek. We used those. These are the weights we got. This graph shows how different the languages actually responded to the different term types. You can see that on our training data, we saw a big difference between words and n-grams. In the test data, there was not a lot of difference. Okay? For French, these are the actual test data from Trek 8, not the training data. So in French, we see that words did much better up at high recall levels, or at low recall levels. N-grams did much better later on. Italian had about the same effect. The German is what's really striking. The German, the n-grams are just absolutely dominant over the words. Why is that? Well, we believe it's because in German, it's perfectly permissible to glom a bunch of words together and get a new word. Okay, they do that all the time. And unless you have a language-specific decompounder, you're not going to be able to handle that with words. Okay, so that's the case where to do word-based retrieval, you really want some language-specific knowledge in there. And if for some reason you can't afford that, you don't have time or you don't have money to put those results in, then the n-grams are just going to perform very much better. So we take these 8 underlying runs, combine them together to get our curve, which was, I guess, good enough to get us second place in the Trek cross-language competition last year. And these results are really interesting. There are the top 3 systems. This is the top IBM system. This is us, and this is the third place 21, which is your European group. It's not really clear that these differences are statistically significant, but it is clear that the 3 systems have their strength in different areas. Right, the 21 system, it just does amazing at low recall levels. The IBM system is nice and healthy here, and from 30% on, we dominate everybody else. Okay, so these techniques that we're developing are once again really good in this part of the curve, and so that means they're good for tasks where you're going to be digging deeply into the data, and you need to see all of the relevant data.
When you give those percentages, they are what?
This is average precision on the task. Okay, so you can see that these numbers are significantly below the best average precision on the English-only ad hoc task was 33%. These are significantly below there, and that has to do with a variety of factors, but probably mostly because it's just a lot noisier going between languages.
Who's 21?
It's a European group. I think it's funded by the whatever that EU. What's that funding? Cross-country funding agency over there. You know what I'm talking about? It's I don't know.
They never gave me any money.
Yeah. Let's see, how are we doing on time? All right, I'll go through this. One of the technologies that we use, we're calling affinity sets. We used to call them cognates, but then we decided that we didn't want to tick off the linguists, because they'd be totally confused. So we're calling them affinity sets. I don't know if that's any better, but the idea is to try to extract, given an input word or phrase, closely related words or phrases. Okay, for example, if you put in computer security, you might like to know that virus and hacker were closely related there. And so we have algorithms to automatically generate these things based on a large collection of text. And they're useful in a variety of ways. here are some sample affinity sets. These are actually, we put in the top phrase, and except for words in that phrase, these are the actual words that we get back in rank order. Okay, so they're pretty good. I mean, you look at Hopkins, of course, neither APL nor Homewood is well represented here, but that's because the collection is a collection of late 80s news articles. So you can see that these sets of related words are actually pretty good. There are lots of uses for these things. We use them, for example, to do what's called automated relevance feedback or blind relevance feedback. It goes under various names. The idea is this. If you have an information retrieval system that is being used by a person, that person can, after documents are retrieved, say, that's a good document, that's not, that's a good document. And once you've got those documents, you can then have the system pull terms out of those documents and add those terms back into the query. And by doing that, you get a marked improvement in the quality of the results upon resubmitting that query. Because users are bad at thinking up all the relevant terms. The observation that leads to blind relevance feedback is that, well, say you don't have a person. All you do is do a retrieval, take your top N documents, pretend they're all relevant, pull important terms out, throw them back into the query, and do another retrieval. This technique has anybody not on the web uses it. On the web, they think it's too slow to do this, so they typically don't do it. But for other systems, you get a huge boost in performance just by doing this. So we use these affinity sets to add to the query. So we'll take the original query, generate its affinity set, add those terms in, and we get a much better query and therefore much better results. So we use that for query expansion. You can use them to summarize or highlight important terms in a document. When you get a document back, you know that if you use a web search engine, sometimes you have to click on the document and look, and you're scanning down trying to find what's important. This will highlight what's important about the document, even if they're not the words that you originally used in your query. Word sense disambiguation is another application. Cross-language information retrieval, and I'll talk about that right now. There are the traditional way for doing cross-language retrieval, and the way that I just described is you have a query, information operations for those of you. I live at APL, and an APL has a lot of Navy sponsors, and so you have to sort of throw around military terms to sound good. So information operations is a military term for what the press at large calls hacking, okay, which we know is not hacking, is cracking. But so this is our input phrase. And what we have done in cross-language retrieval, and what most systems do, is they translate that using a dictionary or a translation software into a query in the foreign language. And then you index in the foreign language and retrieve documents like that. Okay? That's one way to do it. Another way to do it, though, would be to do the following. You take a collection which has documents in two languages, a parallel corpus, if you will. For example, if you're doing French, as in this case, the Canadian Parliament publishes all of their documents in both English and French. And there's a one-to-one correspondence between the documents. Okay? So if you happen to be interested in topics that they're interested in, then what you can do is index the English documents using your basic retrieval system. Do a retrieval in your source language, in English in this case, to get back English documents. Take the corresponding French documents and extract the important words, and then use that as the query. Okay. So in fact, this is work that we have ongoing now. I should probably point out the way we calculate these affinity sets is as follows. We use retrieval to do it. We take the input phrase, we retrieve documents that are relevant to that the system believes are relevant to that phrase. We take the top end documents, and we look at the word frequencies in that sub-collection of documents and compare the word frequencies to the frequencies in the collection as a whole. Okay? Those words that get the biggest boost are the ones we put into this affinity set. Okay? And so if you dig down, that actually ends up being sort of related to mutual information, but it's not mutual information. It turns out for our purposes, this is a little better. But we're actually using retrieval to generate these things. Okay, so we have this approach ongoing now, and we hope that if we can get enough data in a parallel collection, that it'll be useful for retrieval when you don't even know how to translate individual words or sentences. Another thing that we have ongoing is trying to mine the web for these parallel collections, and you've probably all gone out and seen sites that have two different languages. Often one of the languages is English, because until very recently, English was really the lingua franca of the web. That's changing now, but there's still a lot of sites out there that have both English and another language. And so if you can go out and find these things, then you have a ready source of parallel documents. And so we are actually building a web spider that will attempt to do this. Automatically harvest these parallel collections, throw them into that architecture I showed you before, so that we can actually take a new language, plug in an English query, and do retrieval, even without any actual translation software. That's that. Okay, so in conclusion, here are some conclusions. There are probably others. We have found that this hidden Markov model technique, the probabilistic technique that we use, seems to outperform the cosine technique and its derivatives almost uniformly. So if you only get one similarity metric, we would recommend the hidden Markov model. If you get more than one, then use both, because we still find a significant boost by combining the two scores. We find that words are sometimes better, sometimes worse. You have to look at your task, look at what kind of language-specific resources you have, look at the quality of the data, and make an assessment about which one to use if you only get to use one. If you get to use them both, again, combining them improves your performance. We do not believe that cross-language retrieval requires machine translation. That is, we think that there should be enough data available to be able to do basic information retrieval just by using parallel corpora that you glean from somewhere or another, and use this affinity set technique to generate a query in the other language without actually being able to do translation. And finally, what we recommend for everyone is get a haircut. That's it. Questions? Yes?
Try to see how many of your 6 grams actually point to a single word. So, because when you do the translation, for example, I can understand why for German is better, because words are very long. Not only that, they can be composed, because it's going to depend on your translation system. If your translation system just takes words and replaces with synonyms, for example, and is not very natural for the target language, then I guess words would perform better.
Yeah, well, we do see a difference in how well, on a language-by-language basis, whether words work better or n-grams work better. You're certainly pointing to real problems with the system. I should point out that all of these retrievals that we're talking about use the entire Trek topic. So we have a fair amount of text that we're working with. And so even if those problems of slight mistranslations occur in one place, we have enough text there to be able to pull out good terms that we do reasonably well. Okay, we have not tracked down exactly why Italian curves look like this and French curves look like that. We're still, the work I talked about here with the cross-language retrieval was the result of maybe a month's work last summer. So we didn't have time to play around a lot. But you're right, there are a lot of problems with translation. But the interesting thing about information retrieval is that you can get by in an information retrieval setting with much less accuracy than you can in, say, a machine translation setting. Okay? For example, suppose you have a cross-language dictionary, but you don't have a method for determining which of several different translations to select. Okay? In a machine translation setting, you have to have a method, right? You have to make up a method, take the most common, or you make something up. But you have to select one of those. In an information retrieval setting, you can get by and say, oh, I'm going to take them all.
Yes, but you said you use a system, a translation system, and that's going to take just one. That's why I'm concerned. I mean, if you
So
if you use a dictionary, then it was
right, yeah.
That's
So with the
going to pick one of them.
Yeah, so that it picks one, and it's going to pick wrong sometimes. We have a paragraph worth of text. So our hope is that somewhere in that paragraph, the system gets it right, and we get some good terms. And I think our results at least show that we're doing as well as anybody else in using the output of the translation system as it is without trying to do anything to clean it up if it makes mistakes. The point is that information retrieval is much more tolerant of mistakes than a machine translation. Yeah?
I was wondering if there's been any work on getting documents of different languages into sort of a meaningful single similarity.
Yeah. Question is, can you take documents from several languages and put them together in some single space that's meaningful? There are two kinds of work that I know along those lines. Some folks have used singular value decomposition to come up with a unifying semantic space. The other interesting thing was, I can't remember who did this. They simply put all, it was Berkeley. Actually, it was the Berkeley Library School of Berkeley did this. They simply put all of the documents into a single big collection. They took the query, they translated it into the different languages, crammed all those words together, and did retrieval against that. They didn't have to merge at all. It did great. So yes, there are people who have done that. Obviously, the one that's more compelling is the SVD approach. But I'd say the cross-language retrieval state of the art is pretty low. There's a lot of room for improvement. So nobody's really nobody showed a huge boost by using one technique or another. Yep.
I have two questions. One refers to the hidden market model, which I would actually call it more an IE-based model.
It is. That's yes. So with back off, I guess is what they say.
Yes.
Yeah.
The alpha you trained there is the same for all the documents, or is it?
We use a single alpha for all the documents. We use 0.3 for words, 0.15 for n-grams, except when we use 0.3 for n-grams. And our motivation for that is, we don't even really we don't even do that right. All we do is we ran a few runs with different alphas, plotted the curve, and it's really flat. So if 0.3, 0.4, 0.2, they're all going to do about the same. It's just the way it turns out for this task. So it's mind-numbingly stupid, but it works really well.
But have you thought of using different alphas for different documents?
Yes, there's been the folks who originally suggested this from BBN have tried a number of different experiments. I think they or someone else tried that. They tried having many different sources for words. They did wrap phrases in there too. They tried a lot of things. Not a lot worked. This is one of the weird things about information retrieval is that and maybe it's not just information retrieval. It's this way in a lot. It's probably this way in speech. I don't know. But you have 5 techniques, and you think, oh, these techniques are really great. And you throw them in, none of them works, right? That just seems to be the way it is in information retrieval. And so the systems that are successful are the ones that try lots and lots and lots of different techniques until they find that one that works. It's very unprincipled, but us scruffy types don't mind it.
The second question was, what kind of performance price are you getting for using for
Depends on how you measure it. If you're talking about like compute time or time. Using n-grams, you pay a significant performance hit because a given document has more n-grams than it has words. So that is a multiplier of whatever the average word length plus 1 for the space, I guess. So it's like a 5 or 6x penalty in retrieval time. You can ameliorate that somehow, if you want, by stopping words. Stopping is simply a technique of throwing away very high frequency terms or very low frequency terms, which tend not to contribute much to the similarity. You can do that and get it down, but you do pay a penalty there. For the different similarity metrics, there's no penalty.
You have to run all 4 of them, so.
You don't have to run the. If you do it that way, and that's the way we do it because we're playing around with it. Yes, you pay if you do 5 runs a 5x hit. If you have different similarity metrics, though, it's very easy to run those in the same run, produce 2 different files at once. There's no significant performance hit for that. You can even do the linear combination at that time. It's just a more complicated similarity metric. So that for the similarity metrics, it's not a big price. For the different term types, it is because you need a separate index for each term type and separate retrieval for each. So you pay a price both at indexing time and retrieval time.
So do you think this technique can be applied in commercial?
Some of it can. Certainly, if you wanted to have a commercial engine that did cross-language retrieval without having a lot of language expertise in the various languages, I think you're going to have to go with n-grams. All the retrieval systems for non-alphabetic languages use charactergrams. So you have to do that. Commercially, having different similarity metrics, yes, that's very easy, and that they shouldn't pay much of a penalty for that. So I think some of this work can be applied commercially in the web setting. Some of it obviously cannot. There's more to retrieval in the web, though. There are lots of tasks where you want to do retrieval where it's just not a web setting. Okay, thank you.